Webb is truly a civilization-scale mission. It not only changes what we know, but how we think about ourselves.
It will pick up where the Hubble Space Telescope and Spitzer Space Telescopes left off in their capabilities.
And it lets us see out through 13 billion years of cosmic time to look at the first generation of galaxies that formed after the Big Bang.
We'll also look at these worlds out there, exoplanets, that may or may not harbor life.
Every second, the universe stretches farther, holding secrets about how everything began and the mysteries of existence. Our search for understanding takes us from the birth of galaxies and the mysteries of black holes to the possibility of life beyond Earth. Each discovery adds to our cosmic story, showing us what we know and the unknown still waiting to be explored. The beginning of the universe is a fascinating subject that has captured the curiosity of scientists and thinkers for centuries. The most widely accepted theory for the origin of the universe is the Big Bang theory. According to this idea, around 13.8 billion years ago, the universe began as an infinitely small point, a singularity, which then rapidly expanded. This expansion was not an explosion in space, but rather an expansion of space itself. In those first moments, the temperature and density of the universe were extraordinarily high, creating a chaotic environment filled with energy. As the universe expanded, it cooled, allowing subatomic particles to form. These particles eventually combined to create simple atoms like hydrogen and helium. A few 100,000 years later, these gases began to clump together under the force of gravity, eventually leading to the formation of stars and galaxies. This process of coalescence and formation laid the foundation for the rich structure of the universe we see today, with its stars, planets, and galaxies. Other theories have emerged alongside the Big Bang to address questions and phenomena that it does not fully explain. One such theory is the concept of cosmic inflation, proposing that just after the Big Bang, the universe underwent an incredibly rapid expansion, stretching exponentially over a very short period. This inflationary model addresses why the universe appears so homogeneous and isotropic on large scales, despite its complex and clumpy structure on smaller scales. Additionally, some cosmologists are exploring alternatives like the cyclic model, which suggests that the universe undergoes endless cycles of expansion and contraction, or models that involve multiverses, where our universe is just one of many existing simultaneously. Each of these theories contributes to a richer understanding of cosmic origins and invites us to continue exploring the mysteries of our existence within this vast, enigmatic universe. The Big Bang Theory is the leading explanation for the origin of our universe, proposing that it began as an infinitely dense point, often referred to as a singularity, around 13.8 billion years ago. This event marked a dramatic expansion, resulting in the universe as we know it today. It wasn't an explosion in the traditional sense, but rather a rapid stretching of space itself, giving rise to all matter and energy. One of the most compelling pieces of evidence for the Big Bang Theory is the observation of cosmic microwave background radiation. This faint glow fills the universe and is a remnant of the hot, dense state that existed shortly after the initial expansion. Detected in the mid-20th century, this radiation provides a snapshot of the universe when it was just about 300,000 years old. Its uniformity and spectrum match exactly what scientists would expect from a universe that started hot and gradually cooled over time. Another significant supporting detail is the abundance of light elements, such as hydrogen and helium, in the universe. According to the theory, during the first few minutes after the Big Bang, conditions were just right for nuclear fusion, leading to the formation of these fundamental building blocks. Observations reveal that about 75% of our universe is hydrogen, while roughly 25% is helium, which aligns perfectly with predictions made by the Big Bang Theory. Moreover, the expansion of the universe itself offers further evidence. Astronomers like Edwin Hubble observed that distant galaxies are moving away from us, with more distant ones traveling faster. This discovery aligns with the concept of an expanding universe, a fundamental aspect of the Big Bang Theory. All these pieces together paint a complete picture of a universe that has evolved over billions of years, from a hot, dense beginning to the vast cosmos we observe today. Scientists measure the age of the universe using several key methods that intertwine observations and theories. One of the most significant approaches is the study of the cosmic microwave background radiation, often shortened to CMB. This is the afterglow of the Big Bang, a faint remnant that fills the universe. By analyzing the temperature fluctuations in the CMB, researchers can infer the conditions of the early universe. These measurements are crucial because they help us understand the rate of expansion of the universe, known as the Hubble constant, which in turn allows scientists to estimate its age. Another primary method involves observing distant celestial objects. Astronomers look at the oldest stars in our galaxy, particularly those in globular clusters. By determining the chemical composition of these stars and measuring their luminosity and temperature, scientists can estimate how long these stars have been shining, providing a lower limit on the age of the universe. Some of the oldest known stars are around 13 billion years old, reinforcing the notion that the universe must be at least that old. Moreover, the study of the expansion of space itself plays a crucial role. Edwin Hubble's discovery that galaxies are moving away from us indicates that the universe has been expanding since the Big Bang. By applying the laws of physics and measuring the distances and velocities of these galaxies, scientists can create a model of how fast the universe is expanding. When these models are extrapolated backward, they yield an estimated age of approximately 13.8 billion years, a figure that has gained broad acceptance among cosmologists. These methods are cross-validated through various means, including observations from space telescopes and experiments like those conducted by the European Space Agency's Planck satellite. By consistently aligning findings from different approaches, scientists continue to refine their estimates and deepen our understanding of the cosmos. Ultimately, the age of the universe is not just a number. It is a gateway into the history of everything, from the formation of galaxies to the emergence of life on Earth. Cosmic microwave background radiation, often referred to as CMB, is essentially the faint glow left over from the Big Bang. This radiation fills the entire universe and is remarkably uniform, indicating that it originated when the universe was still in its infancy, about 380,000 years after the Big Bang. At that time, the universe cooled sufficiently for atoms to form, allowing photons to travel freely through space. This moment marked a crucial transition from an opaque state to one we can observe today. The significance of CMB lies in the information it provides about the early universe. By studying this ancient light, scientists can glean critical insights into the conditions that existed just after the universe began. The uniformity of the radiation suggests that the early universe was smooth, but tiny fluctuations in temperature can be observed. These fluctuations are key to understanding how matter was distributed shortly after the Big Bang, eventually leading to the formation of galaxies and large-scale structures we see today. Moreover, precise measurements of the CMB have revealed essential parameters of our universe, such as its age and composition. For instance, data from various missions, like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have helped establish that our universe is approximately 13.8 billion years old and consists primarily of dark energy and dark matter. This breakthrough deepens our understanding of the universe's evolution and fate. The cosmic microwave background serves as a cosmic relic, offering a snapshot of the universe's beginnings. It stands as one of the most compelling pieces of evidence supporting the Big Bang theory, allowing scientists to trace back the history of the cosmos and uncover the underlying dynamics that shape it. By analyzing CMB, researchers not only learn about our past, but also refine our predictions about the future of the universe. The Milky Way's halo, on the other hand, extends far beyond the disk and bulge, containing older stars, globular clusters, and dark matter, which still remains mysterious. Dark matter's role is significant, as it constitutes a large portion of the galaxy's total mass, influencing its gravitational structure without emitting light. This component is essential for understanding how galaxies like ours are held together and function. Understanding the formation and structure of the Milky Way not only sheds light on our cosmic neighborhood, but also helps physicists and astronomers explore the broader universe. It opens doors to critical questions about the origin of galaxies and the nature of the universe, revealing that we are part of a much larger cosmic tapestry. The story of our galaxy is a tale of cosmic evolution, marked by stellar births and deaths, all woven together in a grand display of astronomical beauty. The Milky Way galaxy, a vast swirl of stars, gas, and dust, formed about 13.6 billion years ago, shortly after the Big Bang. As matter in the universe began to clump together due to gravity, the first stars ignited, and these early stellar formations played a crucial role in shaping our galaxy. Over time, the Andromeda galaxy, known to scientists as M31, holds a special significance in our cosmic neighborhood, as it is the nearest spiral galaxy to the Milky Way. Situated about 2.5 million light-years away, it represents a point of interest for astronomers seeking to understand the dynamics and evolution of galaxies. Andromeda and the Milky Way are not only close in proximity, but are also on a collision course that will unfold over the next few billion years. This impending collision has profound implications for both galaxies. When these vast collections of stars and interstellar material finally merge, they will likely form a new, larger galaxy. This event, often referred to as the Milky merger, raises exciting questions about galactic evolution and the processes that govern star formation. The interactions between the two galaxies will lead to the reshaping of their structures, potentially triggering bursts of new star creation as gas clouds collide and collapse under gravity. Furthermore, studying Andromeda offers insights into the formation and behavior of galaxies similar to our own. By observing its structure, composition, and motion, scientists can draw parallels and distinctions between Andromeda and the Milky Way, helping to unravel the mysteries of how galaxies evolve over cosmic time. Andromeda contains around 1 trillion stars, a size that dwarfs our own Milky Way, which comprises about 200 billion stars. This stark difference invites curiosity about star density, distribution, and the potential for habitable systems within Andromeda. The Andromeda galaxy is not just a neighboring celestial body. It serves as a vital key to understanding our universe on a larger scale. As we continue to explore Andromeda and monitor its movements, we deepen our understanding of cosmic history and the intricate dance that unfolds across the vast expanse of space. Galaxies, vast systems of stars, gas, dust, and dark matter, can collide with one another due to their mutual gravitational attraction. As galaxies drift through the cosmos, often guided by the invisible pull of dark matter, they can find themselves on a collision course. This process is gradual, taking millions to billions of years. As two galaxies approach, their outer regions start to interact, stretching into long tidal tails, while gravitational forces begin to reshape their structures. The collision itself is not destructive in the way we might imagine, primarily because the distances between individual stars are immense. Most stars won't actually collide. However, the gas within galaxies can collide, triggering bursts of star formation. In the chaos of this interaction, celestial gas clouds can compress, leading to new stars and even forming beautifully intricate structures. For example, when the Milky Way is destined to collide with the Andromeda galaxy in about 4 billion years, it is expected that star formation will surge as gas clouds collide. The consequences of galaxy collisions extend beyond mere star formation. These interactions can lead to the merging of galaxies, resulting in new galactic formations that can take on distinct shapes. Over time, the galaxies may settle into a stable arrangement, often becoming elliptical galaxies, which are less conducive to new star formation compared to their spiral predecessors. Such mergers can also drive the growth of supermassive black holes at the centers of these galaxies, as they feed off the increased gas and stars available during and after the collision. Moreover, these galactic collisions can provoke profound changes in the universe itself. They contribute to cosmic evolution, shaping the cosmic web that dictates the distribution of galaxies across vast distances. Each collision tells a story of galactic growth and transformation, reminding us of the continuous, dynamic nature of the universe, where nothing is ever truly static. In the grand ballet of existence, galaxy collisions are but one of the many intricate moves that highlight the beauty and complexity of the cosmos. Dark matter and dark energy are two of the most significant yet mysterious components of the universe. Together, they make up around 95% of the cosmos, yet they elude direct detection. Dark matter, which accounts for roughly 26%, is an invisible substance that interacts with regular matter through gravity, but does not emit light or energy. Its presence is inferred from the way galaxies rotate and how they cluster together. This unseen mass helps hold galaxies in their gravitational embrace, acting like cosmic glue. Without dark matter, the universe as we know it would not exist. The stars and galaxies would drift apart, unable to maintain their structure. On the other hand, dark energy constitutes about 69% of the universe and has a very different role. Discovered through observations of distant supernovae, dark energy is driving the accelerated expansion of the universe. While dark matter pulls matter together, dark energy pushes it apart. This counterintuitive force affects the universe on the largest scales and is believed to be responsible for the current acceleration of cosmic expansion, shaping the future of galaxies and the universe itself. Understanding these two components is crucial for astronomers and cosmologists as they explore the intricacies of galaxy formation and evolution. The properties of dark matter influence the distribution of galaxies in clusters, guiding our understanding of how these celestial bodies formed in the early universe. Meanwhile, dark energy presents fundamental questions about the fate of the universe, challenging scientists to rethink models of cosmology and the ultimate destiny of everything, from stars to galactic clusters. Dark matter and dark energy are not just ambiguous terms in a glossary of cosmological phenomena. They represent the very fabric of the universe, intricately woven into the histories and dynamics of galaxies. As researchers continue their quest to comprehend these enigmatic forces, they open doors to deeper insights into the workings of the cosmos and our existence within it. Scientists searching for and studying galaxies billions of light-years away rely on a combination of powerful telescopes and advanced imaging techniques. The vast distances in the universe mean that light takes a very long time to reach us, with the light we see from a galaxy billions of light-years away actually being emitted billions of years ago. This means that when astronomers observe these distant galaxies, they are looking back in time, gaining insights into the early stages of galaxy formation and evolution. Telescopes, particularly those situated in space, play a crucial role in this quest. Instruments like the Hubble Space Telescope and the recently launched James Webb Space Telescope can capture light from faraway galaxies by utilizing advanced sensors and imaging technology. These telescopes are designed to detect not just visible light, but also infrared and ultraviolet radiation, allowing scientists to gather a broader spectrum of data. This capability is essential, as many distant galaxies emit light that is redshifted due to the expansion of the universe, meaning their light has shifted toward the red end of the spectrum. Moreover, astronomers combine observations from different wavelengths to build a more comprehensive picture. For instance, infrared observations can reveal how galaxies formed and evolved, while ultraviolet light provides information about star formation rates and the presence of young stars. A black hole is an incredibly dense region in space, where the gravitational pull is so strong that nothing, not even light, can escape from it. This phenomenon occurs when a massive star exhausts its nuclear fuel and can no longer support itself against gravitational collapse. When this happens, the star's core is crushed to an unimaginably small point known as a singularity, surrounded by an event horizon, the boundary beyond which nothing can return. The process of black hole formation begins in the life cycle of a massive star. For stars that start out with a mass more than about 20 times that of our Sun, they eventually enter a stage called a supernova, a colossal explosion that signifies the end of the star's life. During this explosion, the outer layers of the star are blown away, while the core collapses under its own gravity, leading to the formation of a black hole. Interestingly, not all black holes form from the depths of massive stars. Some black holes may be born from the merging of neutron stars, which are even denser remnants of supernova events. In this case, when two neutron stars spiral toward each other and combine, they can create a black hole through their intense gravitational forces. Astronomers have detected gravitational waves, ripples in space-time, created by such cosmic collisions, giving us a fascinating glimpse into the universe's dynamic processes. Today, we know of various types of black holes, including stellar black holes, which are several times more massive than the Sun, and supermassive black holes that reside at the centers of galaxies, with masses equivalent to millions or even billions of suns. The mysteries that surround black holes captivate both scientists and enthusiasts alike, as they challenge our understanding of physics and the fundamental nature of reality. Black holes are some of the most fascinating and extreme objects in the universe, exerting a profound influence on the fabric of space and time around them. At the core of their dramatic effect is a concept rooted in Einstein's theory of general relativity, which visualizes gravity as a curvature of space-time. When a massive star collapses into a black hole, it creates an intense gravitational pull that warps the surrounding space-time, much like a heavy object placed on a taut rubber sheet. As one moves closer to a black hole, this curvature of space-time becomes increasingly pronounced. The region surrounding a black hole is known as the event horizon, which is the point of no return. Once something crosses this threshold, it cannot escape the black hole's grasp. This distortion has fascinating implications for time itself. Observers far away from a black hole would notice that time near the event horizon moves more slowly compared to distant regions of space. This effect, known as time dilation, showcases how deeply black holes can manipulate the passage of time alongside the geometry of space. Furthermore, black holes can influence their surroundings beyond the immediate effects of their gravitational pull. They can drive the accretion of surrounding gas, creating powerful jets of particles that shoot outwards at nearly the speed of light. These jets can reshape nearby materials, creating environments that can affect star formation and galactic evolution. This interplay of energy and gravity creates dynamic systems as matter spirals inward, heating up and emitting radiation that can be detected across vast distances. Black holes are gateways to understanding the universe's most extreme phenomena. They challenge our perception of reality, as they remind us that mass and gravity can warp the very structure of space and time itself. As researchers continue to observe these celestial giants, we uncover new insights into the fundamental laws that govern our universe, revealing the beauty and complexity of nature's design. The event horizon is a crucial concept in the study of black holes. It can be understood as an invisible boundary surrounding a black hole, beyond which no information or matter can escape. Once something crosses this threshold, it cannot return to the outside universe. This unique feature makes black holes fascinating objects of study in astrophysics, as they challenge our understanding of gravity and the nature of time and space. The significance of the event horizon lies in its relationship to the immense gravitational pull exerted by black holes. As an object approaches this boundary, it experiences extreme tidal forces. The intensity of gravity near the event horizon warps space and time, creating conditions that are radically different from those in our familiar universe. For scientists, the event horizon represents not just a limit to what we can observe, but also a gateway to understanding fundamental physics. Moreover, the event horizon plays a vital role in the process of information loss associated with black holes. When stars and gas fall into a black hole, the information about their properties seems to be lost forever, leading to heated debates among physicists. This question touches on the fundamental principles of quantum mechanics and general relativity, pushing researchers to find a unified theory that can explain phenomena at both the cosmic and quantum scales. The event horizon is much more than a mere boundary. It defines the region of no return in a black hole's environment and introduces challenges to our existing theories of physics. Studying this enigmatic feature allows scientists to explore some of the deepest questions about the universe, from the nature of gravity to the interplay between information and reality. Black holes, by their very nature, are fascinating cosmic entities that do not emit light, making them invisible to traditional observation methods. However, scientists have developed clever techniques to detect and measure these mysterious objects through indirect evidence. One of the primary ways to spot a black hole is by observing its effects on nearby stars and gas. When a star orbits a black hole, it often moves in a unique pattern that indicates the presence of an unseen massive object. By measuring this motion, astronomers can estimate the black hole's mass. Another critical method involves the examination of the intense radiation emitted from the accretion disk surrounding a black hole. As matter spirals and toward the event horizon, it accelerates and heats up, generating significant amounts of X-rays and other forms of energy. Telescopes equipped to detect X-ray emissions, like the Chandra X-ray Observatory, can identify these hot, glowing regions. If we see an area in space emitting notable X-rays without a visible star nearby, it can often suggest the presence of a black hole. Gravitational waves also play a vital role in the study of black holes. When two black holes collide, they create ripples in space-time known as gravitational waves. Detectors such as LIGO and Virgo can pick up these waves, allowing scientists to infer details about the black holes involved in the collision, including their masses and spin. This groundbreaking method has opened a new window into the study of not just black holes, but the fundamentals of the universe itself. These innovative detection methods reflect the ingenuity of scientists as they strive to understand what exists beyond our view. Through careful observation of gravitational effects, high-energy missions, and cosmic events, we gain a glimpse into the nature of black holes, enhancing our understanding of the universe's most enigmatic features. The quest to reveal the secrets of black holes continues as we advance our technologies and deepen our knowledge of the cosmos. Supermassive black holes are colossal entities, weighing millions to billions of times the mass of our Sun. They reside at the centers of most galaxies, including our own Milky Way, and their formation is still a subject of intense research. These black holes grow by consuming surrounding gas and dust, merging with other black holes, and absorbing stars that wander too close. This immense gravitational pull allows them to rule over their galactic neighborhoods. Their influence extends far beyond their immediate vicinity, affecting the structure and evolution of their host galaxies. The energy output from materials spiraling into a supermassive black hole can be staggering, often resulting in the formation of powerful jets and radiation that can illuminate the cosmos. Black holes have long fascinated astronomers and physicists, primarily because their interiors challenge our understanding of the universe. At the heart of a black hole lies a region called the singularity. Here, according to current theories, gravitational forces become so intense that they warp space-time to the point where the known laws of physics cease to function reliably. The singularity represents a point of infinite density, where everything that has fallen into the black hole is crushed to an unimaginable point. Beyond the singularity, there are various theoretical models that attempt to describe what might lie inside a black hole. While these ideas remain speculative, they inspire both scientists and the public imagination about the deeper mysteries of black holes. As our tools and theories develop, the quest to unveil the secrets hidden within these cosmic enigmas continues to ignite curiosity about our universe. The birth of a star begins in the heart of a molecular cloud, a vast region of space filled with gas and dust. Within these clouds, regions of higher density can become gravitationally unstable, causing them to collapse under their own weight. As the material gathers, it forms a protostar, where gravity pulls the surrounding gas and dust into a spinning disk. This process is accompanied by an increase in temperature, and within just a few million years, nuclear fusion ignites at the core, marking the transition from a protostar to a main sequence star. Main sequence stars, which include our Sun, spend the majority of their lives fusing hydrogen into helium in their cores. This phase can last for billions of years, depending on the star's mass. Smaller stars, like red dwarfs, have a cooler surface temperature and burn their hydrogen slowly, while larger stars consume their fuel much faster. As they age, these stars will eventually exhaust the hydrogen in their cores, leading to significant changes in their structure and behavior. Once a star runs out of hydrogen, it embarks on a journey through various stages. For moderate-mass stars, this leads to the expansion into a red giant, where helium is fused into heavier elements. After this phase, these stars encounter a dramatic end, shedding their outer layers and leaving behind a dense core called a white dwarf. In the case of massive stars, the end is even more explosive. They may go supernova, a cataclysmic explosion that results in either a neutron star or a black hole, depending on the remaining mass. The life cycle of a star is a remarkable process that shapes the very fabric of the universe. From the gas and dust of a collapsing cloud to the energetic explosions marking the end of a massive star, each stage plays a crucial role in the cosmic ecosystem. This cycle not only forms the stars and planets we see today, but also disseminates essential elements, enriching the interstellar medium and paving the way for new generations of stars and worlds to emerge. A star's lifespan and ultimate fate are primarily determined by its mass, composition, and the way it generates energy. The most significant factor is mass. The greater a star's mass, the faster it consumes its nuclear fuel. Massive stars can burn to their hydrogen reserves in just a few million years, while smaller stars, like our Sun, can thrive for billions of years. This difference in lifespan is a result of how quickly the star's core temperatures and pressures rise, leading to rapid fusion processes. The composition of the star also plays a crucial role. Stars are made mostly of hydrogen and helium, but the presence of heavier elements influences how they evolve. For example, stars with higher metallicity can form dust and planetary systems more readily than those made up primarily of hydrogen. These differences affect not only their lifetimes, but also the types of byproducts they produce at the end of their life cycles. As stars exhaust their fuel, they undergo dramatic changes. A low to intermediate mass star, like the Sun, will expand into a red giant, shed its outer layers, and leave behind a hot core that becomes a white dwarf. In contrast, massive stars can explode in a supernova after forming a neutron star, or even collapse into a black hole. This catastrophic end is a fascinating glimpse into how the universe recycles matter, creating the building blocks for new stars and planets. The lifespan and fate of a star are governed primarily by mass and composition, with their unique evolutionary paths, showcasing the dynamic processes at play in the cosmos. As they burn bright, they contribute to the tapestry of the universe, influencing everything from the formation of elements to the ongoing cycle of star birth and death. Measuring the size and composition of distant stars is a fascinating challenge that scientists have devised clever methods to tackle. One of the primary techniques for understanding a star size is through a method called stellar parallax. This approach involves observing a star from two different points in Earth's orbit around the Sun. By measuring the apparent shift in position against more distant background stars, scientists can calculate the distance to the star. With this distance known, they can employ additional methods to estimate the star size, often using its brightness and temperature. Another key method for determining a star size is through the analysis of its brightness, known as its luminosity. By employing the inverse square law of light, scientists can estimate how far away a star is by measuring the amount of light that reaches Earth. Once distance is established, astronomers can compare the observed brightness to the intrinsic brightness of similar stars to gauge size. If a star is particularly large and bright, its enormous energy output signals that it must indeed be a giant in the universe. In terms of composition, scientists rely heavily on spectroscopy. By dispersing a star's light into a spectrum, they can identify the unique fingerprint of elements the star contains. Each element absorbs and emits light at specific wavelengths, allowing astronomers to determine what materials are present. By examining these spectral lines, scientists can infer not only the star's chemical makeup, but also its temperature, density, mass, and even its age. Finally, advanced telescopes, including space-based observatories like the Hubble Space Telescope, have enhanced our ability to measure both the size and composition of distant stars with greater accuracy. With these tools, astronomers continuously refine their understanding of our universe, revealing a cosmic tapestry of stars that varies vastly in size, age, and composition. Through these dedicated efforts, we inch closer to unraveling the mysteries of the stars that light up our night sky. Neutron stars are the remnants of massive stars that have exhausted their nuclear fuel and undergone a supernova explosion. When such a star collapses under its own gravity, it compresses protons and electrons together to form neutrons, leading to an incredibly dense object. A single teaspoon of neutron star material could weigh as much as 5 billion tons, highlighting the extreme conditions found in these celestial bodies. Despite their small size, typically around 20 kilometers in diameter, they possess a mass greater than that of our Sun. Pulsars are a special type of neutron star that emits beams of electromagnetic radiation, often observed as pulses. These beams are generated due to the star's rapid rotation and strong magnetic fields. As a pulsar spins, the magnetic poles of the neutron star sweep across the sky. If the beam is directed toward Earth, we see a pulse of radiation with incredible precision. Some pulsars rotate hundreds of times a second, making them some of the most stable natural clocks in the universe. Binary star systems consist of two stars that orbit around a common center of gravity, bound together by their mutual gravitational attraction. These stars can be in various configurations. They can be close together or far apart, and their orbits can be circular or elliptical. In many cases, these systems are so closely linked that one star's influence can significantly affect the other's evolution, brightness, and even its ultimate fate. Supernovae are not just spectacular cosmic explosions. They play a crucial role in the life cycle of stars and the evolution of the universe. When a massive star reaches the end of its life, it exhausts the nuclear fuel that has been sustaining its energy output. Without this fuel, the inward gravitational pull outweighs the outward pressure from nuclear fusion, causing the star's core to collapse. This collapse triggers a catastrophic explosion, releasing an immense amount of energy in the form of a supernova. The energy released by a supernova can briefly outshine an entire galaxy. During this powerful event, heavy elements are created and enriched in the stellar environment. Elements like iron, nickel, and even heavier ones such as gold and uranium are formed in the high-energy conditions of the explosion. Once these elements are scattered into space, they contribute to the next generation of stars and planets, participating in the complex processes of cosmic recycling. Supernovae also play an important role in the dynamics of galaxies. The shock waves generated by these explosions can trigger the formation of new stars by compressing nearby gas clouds. In the universe, their origins are still a topic of heated debate. Proposals for their sources range from exotic astrophysical phenomena to even more unconventional theories involving advanced extraterrestrial technologies. Each of these anomalies highlights both the progress and the limits of our scientific endeavor, reminding us that the universe still holds secrets waiting to be uncovered. Space colonization, or the idea of humans living permanently beyond Earth, has moved from the realm of science fiction to serious scientific and engineering discussions. With the growing interest in exploring other celestial bodies, especially Mars and the Moon, steps are being taken to make this extraordinary vision a reality. The potential for colonization rests on the advancement of technologies that allow us not only to reach these destinations, but also to sustain human life there over the long term. One of the primary hurdles we face is the development of reliable transportation systems. Sending humans to Mars or the Moon will require spacecraft that can make long journeys with life support capabilities for months at a time. Spacecraft designs need to improve in reliability and safety to ensure the well-being of astronauts during these extended missions. Additionally, the cost of such missions remains a significant barrier. While advancements in reusable rocket technology have reduced costs, funding remains a crucial factor that relies on both governmental space agencies and private enterprises. Once we arrive at a target location, we encounter the challenge of creating habitats that can support life in hostile environments. For instance, Mars has an atmosphere that is mostly carbon dioxide, and surface temperatures can plummet drastically. Colonies will need sustainable systems for producing food, water, and oxygen. Researchers are exploring innovative methods, such as growing crops in controlled environments and utilizing resources available on these celestial bodies, a concept known as in situ resource utilization. This approach would allow colonists to rely less on supplies sent from Earth. There are also socio-political and psychological aspects to consider. Establishing a community in space must take into account governance, laws, and social structures, which are uncharted territories in this context. We must ensure that individuals can adapt to living in isolation, far from Earth, and effectively work together in close quarters. Overcoming these multifaceted challenges will be essential for ensuring that space colonization remains not merely a dream, but a tangible human undertaking. In recent years, the prospect of mining resources from asteroids and other celestial bodies has shifted from science fiction into the realm of serious scientific and economic discussions. With an estimated $10 quintillion worth of resources floating within our solar system, the potential is vast. Asteroids, in particular, are believed to contain valuable metals like platinum, gold, and rare earth elements. These materials could not only support space missions, but also have significant applications on Earth. Organizations and private companies are developing plans to explore and eventually extract these resources. For instance, NASA has been pioneering missions focused on near-Earth asteroids. Their OSIRIS-RX mission, which successfully collected samples from the asteroid Bennu, is a key example of the agency's ambitions in this field. The collected samples will help scientists understand the composition and history of asteroids, paving the way for future mining efforts. Moreover, companies like Planetary Resources and Deep Space Industries have emerged with visions to tap into these celestial riches. They aim to create a new space economy by developing the necessary technology to locate, mine, and transport resources from asteroids back to Earth or use them to support activities in space. Their plans include prospecting missions, which would identify which asteroids are most resource-rich and suitable for future mining operations. The implications of asteroid mining extend beyond simple resource extraction. By using materials found in space, we could reduce the dependency on mining on Earth, thereby lessening the environmental impact associated with terrestrial mining. This endeavor not only offers the potential to revolutionize our economy, but could also create a sustainable future for space exploration, propelling humanity into a new era of cosmic resource utilization. Space tourism, once a concept confined to science fiction, is poised on the brink of transformation. With companies like SpaceX, Blue Origin, and Virgin Galactic already conducting suborbital flights, we are witnessing the dawn of a new era where ordinary citizens can experience weightlessness and gaze upon Earth from nearly 200 miles above. As technology advances and costs decrease, the experience of traveling into space will likely become more accessible to a broader audience. As space tourism evolves, it could give rise to a multi-billion-dollar industry. Future developments might include longer stays in orbit or even trips to the moon and beyond. Imagine a world where hotel chains cater to guests in low Earth orbit, offering stunning views of the planet while providing a unique vacation experience. These ventures could generate economic growth, creating jobs not only in the aerospace sector, but also in hospitality, transportation, and other ancillary industries. The implications of space tourism extend beyond economics. As more people experience the profound beauty and fragility of our planet from space, there is potential for a shift in perspective regarding environmental issues. Travelers might return home more motivated to advocate for planet preservation and sustainability, having witnessed Earth's vastness and its delicate atmosphere. This could foster a culture of stewardship, inspiring a collective effort toward addressing climate change and resource conservation. Furthermore, the evolution of space tourism may inspire the next generation of scientists, engineers, and explorers. As our society becomes more familiar with the concept of space travel, we could see a surge in interest in STEM fields as young minds dream of building the next spacecraft or devising new technologies for life beyond Earth. In this way, space tourism could serve as both an adventure and a calling, igniting a curiosity that pushes the boundaries of human achievement in the cosmos. As humanity ignites its ambitions for space exploration, a number of ethical considerations come into play regarding how we interact with other celestial bodies and potential extraterrestrial life. Foremost among these concerns is the preservation of the environments we explore. Many argue that when we venture to planets like Mars or moons such as Europa, we carry the responsibility to protect these locations from contamination. This ongoing conversation urges space agencies to develop strict protocols to prevent Earth microbes from interfering with potential alien ecosystems. An equally significant factor involves the search for extraterrestrial intelligence. The question of whether we should make our presence known to other civilizations, should they exist, remains deeply contentious. Some scientists advocate for a cautious approach, proposing that broadcasting our location could pose risks, while others believe that the potential for contact could yield profound benefits for humanity. This dichotomy raises compelling questions about the implications of such interactions, not only for our species, but for any intelligent life we may encounter. The moral implications are further complicated by issues of ownership and resource exploitation. As countries and private entities gear up to harvest resources from asteroids or other celestial bodies, concerns arise about who has the right to claim these resources. This dilemma is mirrored by the challenges Earth faces, such as wealth inequality and environmental degradation. The rules we establish for space sharing could echo our terrestrial mistakes, urging us to tread carefully to foster a cooperative spirit rather than a competitive race for resources. Finally, space exploration has profound implications for our understanding of humanity's place in the universe. The decisions we make now about how to approach other worlds and any sentient beings that may inhabit them will shape not just our future interactions in space, but also our ethical framework on Earth. Engaging in this discourse not only prepares us for potential discoveries, but also encourages a reflective examination of our values as a species. The sky may be the limit for the universe we seek to explore, but the ethical ground we stand on must be firmly considered. Understanding the vastness of the universe and its intricate connection to our spiritual beliefs opens our minds to a deeper sense of purpose. The universe, with all its celestial wonders, mirrors the divine presence, reminding us of our place in the cosmos. Just as space is infinite, so too are the possibilities of our spiritual journey. Stay curious, stay connected, and keep exploring the profound bond between the cosmos and our spirit.